So we were discussing this one. So the reason because of which the powder gets dissolved quickly is that was correctly answered by, I think, Irfan was there. Increase in surface area, right? Because of this increase in surface area, same sugar now can react with large amount of water. If I take a single sugar cube and if I convert that one into powder, the surface area available with this single cube and surface area available with powder that I have converted from the same sugar cube, in powder there is going to be a large surface area available. So that large surface area can react with water more quickly. So this powder gets dissolved faster compared to this uh, coarse or large particle. That is the reason, right? So this one we are going to relate with some hazards. So what hazards are there? Because of this increase in surface area, again if I consider a single large block and small particles made from the same block, here the atmosphere or atmospheric air available for that surface to react will be less. And here, as we have converted same block into smaller particles, now the amount of air availability will be more. So what happens if I or if that availability of air is more, to be precise, the oxygen availability will be more in case of powders, and that oxygen availability will be less when it is a large block. So now because of this more availability of oxygen, there are certain materials. What materials are there? Like aluminium, magnesium, titanium, zirconium and thorium. For these specific materials, when you convert those materials into powder, because of more availability of surface area, more availability of oxygen, a small change in temperature, or if there is friction, or if there is some spark because of friction between the particles, if anything of these happens with those particles, there will be a huge fire with these specific materials. Okay, and this happens because of increase in surface area only. So that is the hazard associated with these specific materials when you convert those materials into powder form. So while handling these materials, that care has to be taken to avoid this fire. So what care has to be taken? Grounding all the equipments that are used for this metal powder processing, then preventing sparks. So there should not be friction or impact between two metal parts so that there won't be any sparking. And last one, avoiding dust clouds, open flames, and chemical reactions. So all these things should not be there. If any of these is there, then there is going to be a huge fire that is going to be completely uncontrollable. Okay, so that hazard is associated with these specific metal powders. Next, compaction. So we discussed metal powder, getting powders from the metals, then mixing that powder with additives, binding materials, lubricants, and all. That is blending. And after blending, next step is compaction. So what we do in compaction, we provide shape or green shape to the product. So there will be a powder that will be mixed in these binding materials, additives, and there it would be like a wet clay, and that has to be formed into shape of the product, and that obtaining shape of the product is nothing but the compaction. Now that compaction could be carried out at room temperature as well as in certain cases at elevated temperature also. Now let's take example shown over here in the sketch A. Now here, uh, as this is a section or half section, this is final product that is to be uh, get out from this compaction process. So if you consider a full sectional, that could be like a uh, hollow cylinder of this much wall thickness. Okay, so that has to be manufactured. So for that one, what process we need to follow, there will be a arrangement consisting of punch at the top, punch at the bottom. There would be one ejection rod that will be helped to take out the product once it has been shaped into desired shape. Then the whole thing will be connected with a die. That die will be having a shape of the, or a die will be having cavity that would be uh, like replica of the product. Whatever product shape you want, that replica has to be made into the die first. So that cavity would be prepared into the die, and it will be filled with the powder and that mixture. So when you fill all the mixture into the cavity using this upper and lower punch, the mixture will be compacted, and once it has been compacted, it will be ejected out of this assembly by this upward movement of the ejector. So this is specific application, right? But let it be any kind of the compaction process, let it be isostatic or any compaction process, the similar steps are going to be followed. What steps are going to be followed? There would be one cavity that would be filled with this mixture, and it will be compacted by applying some external pressure or force. And once it has been compacted to a final shape, it will be taken out, and that is called as green product or green shape, because it is still in a wet form that you can easily break. We haven't heated it to final temperature, it is still at its initial stages, so it is called as green component or green product. Okay, so once you have got that green component or green product, we need to transfer that green shape for further processing. So for further processing could be, this product might have some projections that has to be removed. Okay, it has to be transferred for sintering, that is final heating. And while doing all these processings, as this is a grain shape, it is very much fragile, that can easily break. So a maximum care has to be taken. What happened? Okay. So maximum care has to be taken because this is a fragile one. But still, if you want to have maximum possible strength associated with this product, or if you want to make uh, strong enough so that you can transfer it from one location to other another without worrying of the breakage or damage to the product, so that you can do by increasing compacting pressure. So in this example, there was one upper punch, there was one lower punch, and both punches were moving towards each other under certain pressure. So when you increase this pressure either on upper or lower punch or both punches, the compaction process will be better, and the strength that you can provide to this green component will be more. So that strength you can increase by increasing the compacting pressure. Okay. In this slide, the things that we were discussing, that density and mechanical properties or mechanical strength and all. If I increase density of compaction, there is going to be increase in uh, all the desired properties associated with the product. To relate that one, let's take look of these two sketches. Now, first, the relationship between density of the product that you can get and compaction pressure. This one we can easily relate, right? From the left to right, there is increase in pressure, and from bottom to top, there is increase in density. So when you increase the pressure from 200 to 400, 400 to 600, there is going to be increase in density of the product. That is quite usual, right? When you increase the compaction pressure, density is going to be better. Now, the relationship between this density and other properties, what are the other properties? Tensile strength of the product, elongation, electrical conductivity. Okay, so here we are going to discuss dependence of those three properties on density. Those three properties has been plotted. This first one is tensile strength, second line is conductivity, and third line is elongation. Now you can see all these three lines are having positive slope. Okay, and positive slope means if I increase the density, all these three are going to be increased. So if I increase density, tensile strength will increase, conductivity will increase, percentage elongation will increase. Okay, and that way these properties are going to be uh, controlled by this density, and density is going to be controlled by this compaction pressure. So this compaction pressure plays a vital role deciding final properties of the product, because when you compact it to a maximum density and when you center it, the final properties are going to be much better as you keep on increasing the density. Okay, so these are the various techniques used for compaction. In these two slides, we discussed what is mean by compaction and certain parameters associated with the compaction that we should be uh, considering. And here we are going to take a look of few compaction techniques. The first technique is isostatic pressing. Isostatic pressing is a technique where hydrostatic pressure is used for a compaction. So there will not be any mechanical ram or hammer or something like that used for compaction, but the force or pressure will be applied in the form of hydrostatic pressure. So hydrostatic pressure means either it would be a water, some air or inert gas, or some fluid that will be used to apply the pressure. So what we do in case of this isostatic pressing, there are two techniques. First one is CIP, that is cold isostatic pressing, and second one is HIP, hot isostatic pressing. From the name we can get that the first one carried out at room temperature, second one at certain elevated temperature. Let's discuss first cold isostatic pressing. So what we do in cold isostatic pressing, there will be a mold made up of a flexible material. Okay, mold would be there, that is filled with metal powders and additives, and all that mixture would be filled into the mold, and that mold will be made up of flexible material, and that will be placed in a chamber that is filled with liquid. In cold isostatic pressing, the liquid will be water, so this will be filled with water. And what we will do, we will apply pressure to this water, or we will try to compress the water. So what will happen, as you try to compress the water will try to compress this flexible mold in all the directions uniformly, because it's water that is being compressed. So the water will exert pressure. Whatever pressure we are applying to water, that will be transmitted to this mold in all the direction uniformly. So there will be compaction of product in all the dimensions simultaneously and uniformly. Okay, so that technique is called as cold isostatic pressing. The same example is shown over here. There is a U-shaped cup that is to be formed over here, that you can see. This is a flexible mold made up of rubber. Central rod would be there depending upon the internal opening required, and this would be filled with water, and there would be one pressure source provided over here. So when you increase the pressure on the water will try to compress this mold in all directions simultaneously, so that you will get the product compacted. So this is cold isostatic pressing. In hot isostatic pressing, instead of water, there would be uh, use of either inert gas or vitreous fluid. Those two will be used uh, in hot isostatic pressing, and the remaining process is going to be same. The major difference is the mold material. In case of cold isostatic pressing, the mold material would be a rubber, that could be uh, neoprene, urethane, or PVC, or even elastomer also, but that would be a kind of a rubber. And in hot isostatic pressing, we know that rubber cannot withstand a higher temperature. So instead of rubber, the mold will be made up of metal sheet that is flexible in nature. A thin sheet would be there that would be somewhat flexible, and when you apply pressure, that could compress. Okay, so the mold would be made up of metal sheet, thin metal sheet, and the working fluid would be inert gas or vitreous fluid. That is the difference between cold isostatic pressing and hot isostatic pressing. The hot isostatic pressing has got certain applications. What applications are there? Because of that involvement of temperature, you can get better properties associated with the compacted product. So applications are going to be, you can reduce the internal porosity of the compacted product in hot isostatic pressing. Also, you can improve the properties of that material. How we are going to improve the properties? Because we know that if I reduce the porosity, that means I am going to increase the density, and if there is increase in density, the properties are going to obviously improve. And last one, last application is in tungsten carbide tools and powder metallurgy tool steels. This one we have seen in single point metal cutting. The inserts are made up of or when you manufacture inserts, the powder metallurgy is the technique used to get those inserts. So when you manufacture these tungsten carbide tools or powder metallurgy tool steels, the final densification step is usually a hot isostatic pressing, or that final step will be carried out at certain elevated temperature to impart the better properties. Advantages and disadvantages of the isostatic pressing. What are the advantages? The first advantage, we know that if this is a product that would be compressed in all direction with uniform pressure, so that compaction will be uniform, and if that compaction is uniform, obviously its properties could be better. So uniformity pressure in all directions produce better properties. Second, parts with high length to diameter, that is nothing but the aspect ratio. Okay, the product that is having large length to diameter ratio, such a product can be easily manufactured by using or compacted by using isostatic pressing. Then last advantage is it is capable of handling much larger parts compared to other compacting processes. So even if you are dealing with a large part that has got many more variations, still you can compact it uniformly with uniform properties and uniform compression and all by using this isostatic pressing, because it is a fluid that is going to exert pressure in all directions uniformly. So this is the advantage of the isostatic pressing. Now there are certain limitations as well. What are the limitations? As you will be dealing with large products, wider dimensional tolerances had to be taken care, because if I'm taking it as an advantage of the process that uh, co- variable shapes on large product can be easily produced, but the limitation associated with that one is we need to take care of wider dimensional tolerances also. The next limitation is the equipment cost is usually high compared to other pressing techniques, because everything has to be like made up of some consumable material for that particular product. And once you have uh, or the process will be taking place into a chamber that is filled with water and all, so that assembly making is going to be little bit costlier. So second limitation is cost associated. And last one is, as the process is quite slower, the small production quantities are usually preferred. When that large production requirement is there, usually this technique will be avoided because its production rate is quite low compared to other compacting techniques. So this is all about isostatic pressing, that is the first compacting technique. Second, powder injection molding, that is also called as metal injection molding. So what we do in case of this powder injection molding or metal injection molding, we take powders having particle size less than 10 micrometer. So very fine powder particles has to be there, and that is blended with 25 to 45% of the wax based binder. Why this much binder is required? Because if you take a look of this sketch, through this offer, that mixture will be introduced This is a screw that will be rotating about its axis, and because of rotation of the screw, the material will gradually move in this direction. And because of this process, the mixture has to be better flow properties, and to offer those properties, that much or that wax based binders are usually used. Now the process is like, from here mixture will be introduced to this screw assembly. With rotation of the screw, with certain force, the material will move in this direction and will finally enter this mold. This is actually mold. Okay, this internal cavity is nothing but the shape of the product that is required. So that cavity will be produced in the mold, and it will have one opening that will be connected to this screw assembly. So through this screw assembly, material will be ejected into the mold with certain pressure, and because of that one, in case of this powder injection molding, the density will be almost closer to its raw material, or you can have better or more dense products by using this powder injection molding. Okay, here the materials that you can process using this powder injection molding, and products that you can made or that you can make has been listed over here. The materials that you can use: carbon and stainless steel is there, tool steels are there, copper, bronze, and titanium. So these materials you can use, and what parts you can make: components of watches, small caliber gun barrels, scope rings for rifles, door hinges, and impellers for the sprinkler system. That water sprinkler system example we saw in the last session, that impellers are made using this technique. And then surgical knives, the knives used in surgical operations and all, that are usually made using this technique. So this is second compaction technique, powder injection molding. These are certain advantages associated with this powder injection molding. What are the advantages? Complex shapes having wall thickness as small as 5 mm can be obtained by using this technique. Okay, so this much small wall thickness product can be made easily. And as I mentioned, the density will be almost equal to its raw material. Because of that one, the mechanical properties are nearly equal to wrought product, because density is going to decide the properties, and as you keep increasing density or bring that density near to the raw product, then properties are also going to be equivalent. Then dimensional tolerances are good, high production rates can be achieved. So when that production rates are to be higher, these techniques can be used, because you can see this assembly has got multiple parts. So when material is injected into the cavity, once it cooled down, the mold will be disassembled, product will be taken out, and again by closing the mold, the next cycle could be started quickly. That could not be done with isostatic pressing. So because of that one, in case of this powder injection molding, the production rates could be much higher compared to that isostatic pressing. किती वेळ शिल्लक आहे? ओके, 8 मिनिट. What is the next technique? Forging and rolling. Mm, okay, let's stop over here. We'll discuss this forging, rolling, extrusion, and pressureless compaction. These four, okay, spray deposition is also there. These 5 techniques are remaining that we'll discuss in the tomorrow's session.